Well, hello once again, Machine Shop Math. This video is on rounding and degree of precision and degree of error. There's degree of precision and degree of error in measurements and in calculations. Some calculators give you more decimal places in the screen and some less. The number of decimal places that are displayed on your calculator is your degree of precision. Now, what the computer chip does inside the calculator may be more decimal places, and then they have their own internal algorithms for rounding, etc., etc. Well, for the sake of this course and this video and this discussion, the degree of precision is the smallest increment of measuring, or the number of decimal places that can be displayed. We will get to that later. The degree of error is 1/2 of the degree of precision. Now, I don't care what you were taught by Dr. Strangelove in some physics course, or some math nun in another math course, or what you thought you were told in blueprint reading. I've taught blueprint reading. I know what the book says. That's dimensioning. That's not mathematical calculations. So let's get on with this. For the sake of this course, any of your fractional answers will also have a decimal equivalent. Let's see if I can get my little cursor gizmo going here. Will also have a decimal equivalent to the 5th decimal place, along with the answer. Now, this was also gone over in the syllabus. The syllabus is your contract. This is written in the syllabus. Last fall, I had a student who thought he was smarter than me. Well, he quickly changed his attitude. Now, all that silliness in blueprint reading about whether it's even or odd, there are 4 ways that it discusses on page 24 in the last blueprint reading book I saw. Ignore it for this course. In blueprint reading, you do what they want you to do. That's dimensioning. That's not calculations. You follow that throwaway numbers in decimal places until you're done. You're going to end up scrapping apart. Now, I know what I'm talking about. All right. If we have an answer such as 1/16 of an inch, the decimal equivalent of 1/16 is 625 10,000ths. Okay, it's 0.0625. The 5th decimal place, this is 1, 2, 3, 4. We said 5 decimal places, but in this case, the 5th decimal place is a 0. So you don't need to put the 0 on the end of it unless you just really want to. Now, I always put a 0 in front of the decimal point where I started. I'd gotten into that habit gazillion million years ago when we were using clay tablets to write down our engineering calculations. If there's a 0 there, it lets me know I need to look for a decimal point. All right. So the answer for 1/16 decimal equivalent, you just divide 1 by 16. Use your calculator. And it is 0.0625. Now let's do 9/64. That decimal equivalent is 0.140625. So 1, 2, 3, 4, 5, 6. There's 6 decimal places there. Now we want to round this to 5 decimal places. So by doing that, our output, our final answer would be 0.14063. The 6th decimal place was a 5. Therefore, round the 5th number up by 1. Again, I don't care what you were told in blueprint reading. If you were to hold to 5 decimal places in the final answer, then look at the 6th decimal place. If the 6th decimal place is a 5 or greater, then the fifth decimal place number is increased by 1. If the sixth decimal place is less than 5, then the fifth decimal does not change. Or you can leave it to 6 decimal places in your answer if you want. If I'm doing the calculations, I will most likely do that. That way I know where I'm going, up or down. But that's just me. I'm kind of anal and weird that way. But for the sake of this course, if you're going to hold it to 5 decimal places, if the 6th decimal place is a 5 or greater, you round the fifth number of the 5th decimal place up by 1. If it's less than 5, you can ignore the 5th decimal number. Again, my advice when you're doing trigonometry calculations and a long string of calculations is you use as many decimal places as you can possibly stomach until you get to the final answer. Then you can round your final answer. If you start throwing away stuff and you start compounding your answers before you get to the final answer, you may be off. All right, and again, I do not care what you thought you were told in blueprint reading under decimal dimensioning. This is mathematical calculations, not dimensioning. You need to use as many decimal places as you can during a string of calculations. I've just said that until you get the final answer. Once the final answer is derived, then based upon the required degree of precision, that is when you will round to the required number of decimal places. More is better, trust me. You can always take more material off. You can't add it back. This is especially important when doing trigonometry calculations. I'll give you an example. If I have a 1/4 inch group at 100 yards, I essentially have a 2.5 inch group at 1,000 yards with my long range prone rifle. The X ring at 1,000 yards is 5 inches. I want to hold half of that X ring to compensate for the mirage, the wind, anything else. So I want that as tight as I possibly can. So when I'm doing my ballistic calculations, I carry those numbers out to at least 5 to 6 decimal places, even though I'm not going to see it on the target. But if I start out precise, if I aim small, I'm going to miss small. You've probably heard that before. So be as precise as you can. If you're a machinist or a field service tech, especially in industrial electronics, you want to be as precise as you possibly can until you get to the very end of the rodeo. Then you can figure out what the final answer degree of precision needs to be. But until then, I would be very fat with my calculations. Use as many decimal places as you can stand. All right, so let's look at degree of precision. This is a conventional tape measure. Well, this is in decimal land down here. We're going to ignore that. And we're up here in normal land. All right, the image below of the tape measure shows a degree of precision of 1/16 of an inch. Why is that? Because it's graded, and it's the smallest gradations is 16. See? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 2/16 is an eighth, 4/16 is a quarter, 4 over 16, put it in your calculator and you'll get 0.25, right? 4 goes into 1, 4, 1, and it goes, 4 goes into 16, 4 times, all right, and so forth and so on. There are 16 1/16 inch marks per inch. That's 16 over 16 equals 1. And since our units of value are in inches, our answer really should be 1 inch. Not just 1, so that could be what? 1 year, 1 furlong per fortnight? Unit of measure. Okay. Right before you get to the next whole inch on this would be what? 2 and 15/16, right? See, 2, there's 3, we ain't there yet. and 15/16. We go 1/16 more, 16th over 16, that's the next whole 1 inch mark, which in this case, in this image, is 3 inches. This is pretty simple, right? Okay, all right. We've figured out how we're going to round our numbers, right? I'm not going to get a lecture through email from some student explaining to me how I need to be a better engineer. That didn't go well for that individual last semester. All right. Let's see. So, the degree of error. What about the degree of error in this? Now, when I'm doing cabinet work, and I've redone my kitchen several times, rebuilt cabinets, stuff like that, theoretically, if you're really good and you're not old and shaky like me, you could have a fine pencil mark in between the 16ths, right? Right in there. I can't believe I did that. Okay, well, I was able to do it. All right, so theoretically, from that 2/16 to 3/16 would be a half of a 16th. Well, that would be 1, 2, 3, 4, 5 30-seconds, right? So that right there would be theoretically 5. Oh, that was a nasty 5. 30 seconds. Right? Okay. Depends on how good you are, how good your eyes are. I have to use trifocus now, so I don't know. Anyway, I think I got my point across. So even though each one of these marks is the degree of precision, half of that's the degree of error. So theoretically, if you're really, really good, you could measure to a 5 30-seconds. All right. Okay. Now, in cabinet work, that's probably okay, 5 30-seconds. Regular carpentry work ain't gonna work. It's too precise. If there is such a thing as too precise. In my opinion, there's nothing. No such thing as too precise. Now, the same goes for precision machining measuring tools. If the caliper is designed for a precision of 0.001 inch, then the error would be 0.0005 inches, half of this. That's if you could see it. The degree of precision will be marked on the tool or in the documentation for the tool. In this case, you can't really see it here, but this dial caliper is marked on the face at 0.001, typical 1,000ths dial caliper. All right. And the manual micrometer, which is this over here, which also happens to be a vernier micrometer. Now, you can buy micrometers that don't have a vernier scale up here. Why you would do that, I don't know. And then they're only good to the same as a dial caliper, only to 0.001, 1,000th of an inch. And why you would spend the money for a micrometer and not get a vernier, I have no earthly idea. But they do sell them. I wouldn't buy one. Okay. All right, so then the degree of precision, we've already done that, degree of error. So the degree of precision will be marked on the tool and or on the documentation. You can see this is marked down here, okay? And if this image was bigger, you would see it marked right in there, okay? All right. You will learn how to read these in basic machine shop. The manual mic is more precise because it has a vernier scale. The vernier scale is named after a mathematician, Vernier, and so French mathematician by the name of Vernier, ancient days of yore. When England and France were fighting back in the ancient days of yore, they didn't call the vernier scale a vernier scale. They called it a nonius because they didn't want to pay homage to the French. All right. Bunch of silly people in Europe. Okay. No, humans hadn't changed. All right. And so, but you can't see the vernier scale. Well, you can barely start seeing the marks here on top. But you'll learn how to read these in basic machine shop. All right. And you'll go through degree of precision, degree of error, and least material condition and most material, maximum material condition and blueprint reading, etc., etc. Are you better? Or you should. Okay. Digital calipers in mics, as shown below, can be designed for a higher degree of precision. All right. This is a digital caliper. And as you can see, it's 1, 2, 3, 4. 4 decimal places on the screen. Wow, that's pretty cool. The digital caliper is not marked. This particular one, Mitotomo, I've got this exact caliper. And it's very accurate, very good. Well, I've got several digital calipers, but it's not marked on the face or on the back of its degree of precision, and it's in the documentation. But Stevie Wonder should be able to see that it's good to 1, 2, 3, 4 decimal places. Now, what about that 4th decimal place? Well, that's your degree of error mark. Okay, half of 1/1000 is what? It's 0.0005. All right. The caliper's 4th decimal place is the degree of error. It's plus or minus 0.0005. This thing will round up at greater than 5 to the next higher 3rd decimal place. So it could show 7325. And then the next unit, next little fraction of a measurement above that 5th place in here, it's going to jump this to 733. Okay? All right. So it could show 0.7325. Then it would jump to 0.732. I just screwed up. I can't believe this. It wouldn't jump to 6. Oh my God. I got to redo this. Anyway, it would go to 0. Well, here, let's do something a little better. Oh my goodness. My goodness gracious alive. Well, I can fix this, I think. Yeah, I can fix this. I can fix this. Yeah. It would jump from 7325 to 7330. Oh my goodness, I can't believe I did this. Well, everybody makes mistakes, man. I should have had my wife look at this or something and proof it. Let me save this over here. Okay, all right. Okay, well, I'll replace the one I stuck in D2L with this one. All right, let's move on. See if I screwed something else up. All right, this is a digital micrometer. All right, and as we can see, oh, I love it. As we can see, it's good to what? There's your 0, there's your decimal place start point. 1, 2, 3, 4, 5 decimal places. So the digital mic is marked to 5 decimal places. Now I also stuck it on the face up here at 0.00005. Okay. The 5th decimal place is the degree of error for the sake of this discussion. It means it's going to go to just 5, and it'll go up or it'll disappear. It can stay at 5. It'll go to 12210, 12215, or it would go to 12220. See, it would go 1220. At least I got that right. All right, and then from there it could jump to 12225, and so on and so forth. Does that make sense? If I haven't confused you by now. Okay. Well, I will put this up on D2L since I fixed it, and we will see you on the next video. Now, as long as this one's been going on. Oh, not very long. Not even 20 minutes. Okay. So again, rounding is the big deal. You give me an answer, a fraction only, I'm going to count it wrong. I want every fractional answer with a decimal equivalent. Because some of those long fractional problems on the exams, there are several ways that you can give that answer depending on how you work your fractions out. But the decimal equivalent will still be the same once you reduce it to the decimal equivalent. So, all right? If you have any questions, you can email me. All right, I'll see you on the next video.